Hello, my name is Junyao and I'm a PhD student at the GRASP Robotics Lab of the University of Pennsylvania. I'm here to present POCR, composing pre-trained object-centric representations for robotics from what and where foundation models. Recently, pre-trained representations for robotics, which embeds image input into a flat vector, are fast becoming the standard encoder for vision-based robot learning. This is because they can be flexibly deployed off the shelf and do not require large amounts of task-specific data. However, these flat pre-trained representations don't explicitly capture discrete and meaningful entities. Therefore, they struggle with tasks that require multi-object reasoning, object affordances, and object geometries. Object-centric embeddings, or OCEs, on the other hand, capture objects by summarizing the scene with discrete entity slots. For each entity, they capture the where information or location and the what information or content. However, existing OCEs must be trained in domain with a lot of data and often struggles out of domain, and in complex settings, state-of-the-art OCEs perform poorly even in domain. Therefore, we ask, how can we get the best of both worlds by building functional and practical pre-trained OCEs for robotics? In this work, we take inspiration from recent advances in foundation models to build better representations for robotics. We view recently proposed pre-trained representations for robotics as what foundation model for describing image content. We view recently proposed pre-trained segmentation models as where foundation model for describing object locations. And our key idea is to appropriately chain these foundation models together to create POCR, a new pre-trained object-centric representation for robotics. POCR has three key components that address three key questions of vision-based robot learning. Where are the relevant objects? What are their contents? And how should robots act to perform tasks given the what-where representations? First, POCR represents the location of each object. Pre-trained segmentation models are known to suffer from over-segmentation of irrelevant background and overlapping objects, as well as temporal inconsistency throughout a video. To address the first issue, we use foreground entity screening and non-segment suppression to filter over-segmentation of the scene. Here on the left, we see that in the raw output of a general-purpose segmentation model, there are numerous overlapping and background masks. On the right, we see that after our procedure, irrelevant over-segmentations are removed. And to address the second issue, we use a Hungarian matching scheme with Dino V2 features to bind objects to temporally consistent slots. Next, POCR represents the content of each object. We first take a masked image of each object, as shown in the figure, and pass it to a pre-trained visual encoder to obtain its pre-trained embeddings. We then concatenate the pre-trained embeddings of the masked image with its corresponding masked bounding box coordinates, and together they form the visual vector representations of a masked image in each object slot. Finally, POCR learns robot policies. We use a self-attention layer that encodes permutation invariants to process the slot vector descriptors. Then we use MLP layers to learn robot actions with a behavior cloning objective. To evaluate our method, we performed experiments on 7 simulation tasks and 3 real-world tasks. In simulation, we have pick up cup and put rubbish in bin, which are multi-object tasks with destructors. We also have stack wine, phone on base, and water plants, which are multi-object tasks requiring reasoning about object geometries. And finally, we have closed box and closed laptop, which are articulated object tasks requiring reasoning about object affordances. In the real world, we have put apple, eggplant, pineapple in green pot, 3 multi-object pick-and-place tasks with a variety of destructors in the kitchen scene. POCR performs consistent and accurate object localization. Here are some selected frames from the real-world task eggplant in green pot, and we see that POCR localizes objects accurately and binds them to slots in a temporally consistent way. POCR also enables better behavior cloning than state-of-the-art pre-trained and object-centric representations. In this table, we compare the best variant of POCR using SAM as the where model and live as the what model, or SAM-live, with several baselines. Live, R3M, and ResNet pre-trained on ImageNet are the pre-trained representations baselines. And VMA is an object-centric representation baseline. We also compare it to training a convolutional neural network from scratch. And throughout 6 out of the 7 simulation tasks, POCR significantly outperforms all the baselines. POCR also outperforms prior methods on real robot imitation learning tasks. We compare POCR with LIV, the best performing prior method, both with and without data augmentation. We observed that without data augmentation, LIV completely fails in our low data regime, while POCR, the orange bars, still achieve non-trivial performance. With data augmentation, POCR, the blue bars, once again easily outperforms LIV, the red bars. Here are some videos showcasing the successful policies learned by POCR. Finally, POCR enables systematic generalization to unseen test time variations. We introduce unseen distractor objects and background in both real-world and simulation environments, and we observe that in each of these settings, POCR is largely unaffected, but the baseline LIV performs significantly worse. To sum up, POCR is at once a zero-shot off-the-shelf object-centric representation for robotic control, enables better policy learning in both simulation and real world, and achieves systematic generalization to unseen test time variation. We encourage you to check out our paper and our website for more details by going to the link below or scanning the QR code. Thank you.